let's get started. So I made some updates to the DBC archive. So you want to go to the course website, go to the actual GitHub page again, and just download the, go to the DBC archives directory 2017. So 9 minutes ago, I updated this sds22.dbc as well as the extra resources.dbc. So you want to grab both of them and then upload them into your right directories here as usual. So in your community edition, you want to download it to your laptop and then import it here. And the archive file, also you want to import it to the same directory. So you should have this extra resources from the parts. So we'll see if we can get to distributed linear algebra, and let's see how we go today. So I'm going to let you guys listen into some videos first, just to make sure we're all on the same page. I assume that at least a good chunk of you, maybe half of you, are taking courses in machine learning. So this is something you should be really learning in another course. But just to make sure everyone is on the same page, let's watch some videos. Okay. So we did this last time, right? So you guys watch Amit's video toward the end. This is this almost 11-minute video. So now what I want to do is to get your hands a bit dirty by implementing things in Scala Breeze. So this is essentially a linear algebra package for Scala. It's part of the natural language processing tools. So here we will simply implement the concepts in the video from yesterday. Right? And toward the end, I'll try to get you guys into a visual understanding of matrix arithmetic, what it means actually. So now let's just first import Breeze. And if you know, by the way, this is how you would do LaTeX in Markdown, right? So if you want inline LaTeXing, it's // open parentheses, and then you can use math bold font A, that's capital bold A. And if you want, separate formulae, you do $, and then inside there you just write pure LaTeX, right? This is begin parenthetical matrix, P matrix, and then unfortunately you have to skip the underscores. It's some LuaTeX and KaTeX, and I don't know. But anyway, in case you need to use formulae for your presentation in your project, it's not too hard. Okay, so we saw that the bold A is essentially how we represent the matrix, and then lowercase a is subscripted by the row and column indices. That's how you denote each entry. So this is all just from Amit's video, just LaTeXed up. And here we have an example matrix, 1, 2, 3, 4, 5, 6. So in Scala Breeze, you would just say dense matrix, open parentheses, 1, 2, 3, 4, 5, 6. So this will create two rows. The first row is 1, 2, 3, and the second row is 4, 5, 6. It's a 2 by 3 matrix. You can ask what's the size of A. So this is simply the number of entries in A. Are you okay? Should I slow down, or you're all in sync? Okay. So then A dot rows is just another method that tells you the total number of rows of this matrix, right? So there is no method for A dot columns, I believe. So A dot size divided by A dot rows gives you the number of columns.
You can just use A dot cols.
Oh, can you do this?
Yeah.
Oh, okay. Right. Oh, okay, that's good. Yeah, so there was a reason why I didn't. Yeah, that's right. There was a reason because the natural orientation for matrices in Scala is row orientation. So, for example, to make a row vector, later on we'll see, you have to actually use a matrix with one row, right? Because the vector objects in Scala breeze are column oriented naturally. That was good. False. So then let's access the elements like this. So again, indexing starts from 0 like Python, not like MATLAB. Does indexing start with 1 or 0 in R? 1. Okay, so MATLAB and R are this 1, and Python and Scala breeze are 0 indexing. Okay, so now let us make an immutable matrix with var b equals dense matrix. So now we can actually change the entries in place. So I'm rewriting 0, 0 to be 999 and 1, 1 to be 969 and so on. So now that's immutable matrix. So these are just like, I'm literally going through Amit's slides like seconds by seconds. Okay, the next 31 seconds he's talking about the following concepts, right? Vectors, column vectors. So bold A is just a column vector, and A sub I will be the ith entry of the column vector. And we say A is an element of R to the M, where R is just the real in M dimensions, so just a product, Cartesian product of M real lines is R to the M. And so we say A is an element of Rm. So now A is just this dense vector 3.3, 1.0, 6.3, 3.6 of doubles. So here it just does type inference directly because we put the dot operators. So we can do A dot size to be 4. A of 1 will give us the second element of A. So now I can also say A is the dense vector explicitly type specified as double, and then I can put just this integer looking things, right? So it'll still cast it as 5.0, 4.0, and negative 1.0 because that's an explicit type requirement. So now A is a dense vector, 5.0, 4.0, negative 4.0. This one, it does the type inference automatically for you because of the point 0. So unlike MATLAB, you cannot just leave it as a dot, right? MATLAB assumes it's a dot 0 if you just put a dot after 5, but here you have to say explicitly 5.0. Yeah, this is just a recall from the first Scala crash course. So now we can just define a dense vector of zeros of type double of length 5. So is this a column vector or a row vector? Quiz. Column vector, right? Because the column orientation is the natural orientation. Okay, and then Amit talked in the next 1 minute and 2 seconds about various things, including transpose. So this is again for the linear algebraically rusty, right? So if you want, you can rewatch the video, but we watched it yesterday. So here we have creating a dense matrix. It's a 3 by 2 matrix, 3 rows and 2 columns, and it type infers as an integer matrix. So if you do dot t operator, we get the transpose of A, right? So the rows become columns, and so now I can say an immutable val A is the dense vector 3, 4, 1. Then I can also ask what is the transpose of A, right? So this is simply going to give me a transpose. Okay, vector addition and subtraction, or matrix addition and subtraction. So so are you guys, at least in 2 and 3 dimensions, understand the meaning of vector arithmetic, matrix arithmetic? Okay, so when you add 2 vectors, what does it mean in the Cartesian coordinates? So I have 2 vectors, right? This is 0, 0, and 2b.
You move as if you are moving.
Okay, so he got it. So it's the diagonal of the parallelogram that you get by completing the vector, right? That's vector addition in 2 dimensions. What is vector scalar multiplication? If you take a vector and multiply it by 1, you just get it back, right? Nothing happens. But if you multiply it by 2, then it just elongates, right? Okay, you just change the norm. What if you multiply by -1? It just flips and goes the other way. Okay, good. What about 3 dimensions? If you have 3 vectors in R3, and what is the sum of the 3 vectors in R3? Yeah, there you go. This is Costa Rica, right? Yeah, it's the diagonal of the parallelepiped spanned by the 3 sides of the parallelepiped, right? The 3-dimensional parallelogram. That's right. And again, scalar multiplication is the same. And so now, what is now the? So you take a matrix. So you can think of the, let's say we think of the rows of the matrix, or sorry, the columns of the matrix as 3 vectors now, right? So say I multiply this matrix with a vector from the right, okay? So my right. So then, you know, in Namit's video, you saw that it's like this, you know, there's a dot product being done to every row of the matrix, right? What does that mean geometrically? Hmm? I can hear
rotation.
Rotation? No, I wouldn't think. Okay, maybe, but I'm okay. I'm actually more being super explicit. So the first column of this matrix is this vector, right? Second column is this vector, and third is this vector. It's fixed, and I'm actually anchoring them at 0, 0, 0. Okay, right. So now I have my other vector I want to right multiply. So I take the first entry of the vector, right? And then I multiply it by the first vector, second entry. Yeah, I mean, basically I shrink each vector by the weights, and then I just look at the diagonal of the parallelepiped that comes from shrinking each side of the original parallelepiped, right? I mean, this is one embedding, right? But you can do others. This is the usual one, right? So that's what a matrix vector arithmetic is. And so what you get in the end is the diagonal of the parallelepiped that has been shrunk by these things on the right that are hitting it, right? So yeah, you can kind of go like that. And with 2 and 3 dimensions, it's important to visualize it, right? It's hard to understand what it means in higher dimensions. Okay, so this is a dense matrix, 1, 4, 6, 1, 3, 5. And, you know, and then I can say val B is negative of A. And I can do A plus B, it should be 0, right? So I'm just, right, just, because these are, so you can, yeah, you can just imagine like vectors, A representing A, vectors representing B, and you're doing these arithmetic. So there is geometry and some kind of cartoons happening under the hood, right? Actually, literally animation is just linear algebra. Okay, so now, there is a lot more operators. We run out of time, but I sort of got this linear algebra cheat sheet. Hopefully this should just, so if you right click and open in a new tab, this should work if you uploaded everything in the right way. So this is just a wget-k of the linear algebra and then pandoff HTML to markdown. So I just grab this whole thing with all the absolute links and use pandoff to spit it into markdown, and I use vi to do some manual edits. So you sort of get this thing here. It's just really coming from here. Okay. So, I mean, this is just to get you guys really into it a bit more. I don't want to get into it now. But please do it if you want to learn more about linear algebra, and more importantly, babbling between Breeze, MATLAB, NumPy, and things like this, which will happen in practice. But you need to do this. So this is quite helpful because you can see all the syntax side by side for standard operations. Okay, and then there was dot product, matrix vector multiplications, and so on. So let's continue with that. So again, I declare a dense matrix A. That's a 3 by 2, and then I just do multiplication. So this one just gives me element-wise multiplication, right? And of course, element-wise multiplication is commutative, so 5 times A is 8 times 5. This is my dot product, so I first have a dense matrix, and then I have another dense matrix B, and then I have to do this star colon star to get the element-wise product, right? 3 times 1 is 3, 4 times 1 is 4, 6 times 2 is 12, 3 times 1 is 3, and so on. 5 times 3 is 15. So I think in MATLAB that's a dot star, is it? Yeah. R, does anyone know what element-wise? Just a star. So anyway, this is just syntax. So matrix vector multiplication. So we have A, and then we have a column vector. So now so this is what I meant by, this is basically the diagonal of the shrunk parallelogram, where the shrinking is done by this, leaving it alone and flipping. Okay, so matrix multiplication, again, so dense matrix A, B, and just the A times B, right? So this is basically now we have the row of A and the column of B doing dot products on one another, right? So this is a bit more delicate because depending on how you see it, means some things. So you can still think of this as each column of the second matrix basically, shrinking or flipping the, the 3 columns, let's say all the columns of the first matrix and going after the vector, but then doing it many times, ensemble. Anyway, this is the first entry, so let's just check that that's correct. A times B is 46, and that's just 1 times 4, 2 times 9. Identity matrix, this is basically our unity. So if you multiply a matrix A by the identity, which we call dense matrix dot I, type int 3, so that's identity. Let's just visualize this guy, Control C. So this should be the diagonal matrix. 1, 1, 1, right? So if you multiply this by anything, then it'll just leave the original thing alone, right? Okay, so so this is multiplying it the other way, but when we multiply the other way, we just have to make sure the dimensions match up. Okay. Inverses, let's see, D, dense matrix, and you can just ask inv of D. So what is the geometric interpretation of the inverse of a matrix that is square? How do you, I don't know, what is the Ukrainian story for this? What is the inverse of a square matrix in 2 dimensions?
This is calculation.
Yeah, so you have this object called the determinant, right?
Mm-hmm.
And so if you multiply a matrix by its inverse, which is another matrix, then you get the identity back, right? Yeah. So depending on how you visualize this, yeah, it has a notion of a signed volume actually. So the determinant, tells you something about the volume of the parallelepiped. It's actually a signed volume. So D times D inverse is 1, 0, 0, 1. D inverse times D is again the same, right? So now we have Euclidean distances and norms. It's just in a vector, how long it is. It's basically the norm. So you basically have to do the Pythagorean theorem, right? You take each coordinate, square it, and then sum, and then square root, right? So it's the literally the diagonal of the square composed by the sides of these things. So let's create a dense vector V and then ask what its norm is. So that should be 16 plus 9, which is 16 plus 9 is 25, right? Yeah, square root of 25 is 5. It's good. So when you program a lot, I forget arithmetic, so it comes back. Okay, so that's what that is. Now, so yeah.
So this function is just Euclidean.
Yeah, it's just the Euclidean one. I think if you want the.
Because in MATLAB, if you pass the additional arguments.
Yeah, I believe there should be, right? I think I'm pretty sure there must be arguments for norm. I don't know, I'm pretty sure there should be some arguments, but you should find out because there's L1 norm and yeah, I don't know. I haven't dug into the norms here, but I suspect there should be because in machine learning library, which overloads all this, there's all sorts of norms. Okay, so this is homework. I think this is the one I believe. Yeah, let's see if this still exists. So it's the other problem in this world. Okay, it still exists because this actually superseded something else that was Scalala or something. Anyway, now it's Breeze. So yeah, I kind of marked this down mainly for you guys, but anyway, this, yeah, so knock yourself out. It's not assigned homework or anything. Yeah. Let's see. Yeah, actually, there are more sophisticated notions and yeah, there's optimization as well, which we don't have time to get into. So there's a Scala Breeze optimization library. We will watch some videos about it soonish, but yeah, it's linear optimization. What else? Yeah, there's Breeze Viz for visualization. So, try and get into this so you're still in the same language. Again, once you register a table, remember you can babble into Python or R and come back, or actually stay in the same place just for visualizations and things. But you can do quite a lot in Scala Breeze as well. So, and yes, this on cheat sheets and a bit more on data structures. Now, what I would like you to do is to watch this video next. So we haven't watched any videos so far now, right? Since we started?
No.
Okay, so let me try to